Section 3.1 is on solving systems of equations. As you'll recall from Algebra 1, a system of equations is two or more equations with the same variables. To solve a system of equations means to find the values of the variables that make all the equations true. And we have three methods of solving. The first is graphing, the second substitution, and elimination. So let's take a look at an example of graphing. This says solve the system of equations by graphing. We have the equation x plus y equals 3 and the equation negative 2x plus y equals negative 6. In order to make these easier to graph, we're going to put them into slope-intercept form. So my first one becomes y equals negative x plus 3, and my second equation becomes y equals 2x minus 6. So I think I'll do those in different colors so they kind of stand out. I'll do the first one in pink. So I have a y-intercept of 3 and a slope of negative 1. And one thing that's really important when you're solving a system of equations by graphing, I think, is to make all of the dots, because we are looking for that exact point where they cross each other. And in fact, maybe I'm just going to leave it as dots for right now. I'll do my second one in blue. That's y equals 2x minus 6. So I'm going to start with my y-intercept of negative 6. And my slope is 2, so up 2 and right 1. And I'm going to move in the direction of the other line because I'm looking for that point right there, exactly where they cross each other. So I'll go ahead and complete this line. And just so it looks kind of nice, I'll go ahead and draw my pink line as well. And we are looking for that point right there where they intersect each other, and that is the point 3, 0. So that is the solution to that system of equations. Recall that means that when x is 0, or x is 3 and y is 0, both of those equations are true. If the two lines intersect in one point, there is one solution, and we call the lines consistent and independent. If the two lines are the same, there are infinitely many solutions, and they are consistent and dependent. If the two lines are parallel, then there is no solution and they are inconsistent to each other. Here's a little table from your textbook that shows that intersecting lines, one solution, consistent and dependent. If the two equations are exactly the same line, there are infinitely many solutions and the system is consistent and dependent. And if the lines are parallel, there is no solution and the system is inconsistent. Recall that the second way to solve a system of equations is by using substitution. This works well when one of your variables has a coefficient of 1. Here I have 5x minus 3y equals 23 and 2x plus y equals 7. So I'm going to rewrite my second equation in terms of, and solve it for y in terms of x, because my coefficient of y is 1. So y equals negative 2x plus 7. And what I'm going to do with that is, since y is equal to negative 2x plus 7, I'm going to substitute that into the other equation for y. That's why this is called substitution. So now I'll have 5x minus 3 times y, which is negative 2x plus 7, equals 23. Now I have an equation that doesn't have an x and a y in it, but it just has x's. So let's go ahead and solve that. So 5x plus 6x minus 21 equals 23, or 11x equals, adding 21 to both sides, 44, or x is equal to 4. Now I can take that 4 for x and plug it into either of my equations, actually any three of those. Actually, I think I will plug it into here for x. So y equals negative 2 times x, which is 4, plus 7, or negative 8 plus 7, or y equals negative 1. And my final answer is the ordered pair 4, negative 1. Recall again that that is the x and the y that make both of those equations true. And actually you could check by plugging in 4 for x and negative y for 1 into each equation and make sure that both are true. And a third way to solve a system of equations is by using elimination. Recall that this means we want to add or subtract the two equations in order to eliminate one of the variables. So here we have 8x minus 3y equals negative 11, 5x plus 2y equals negative 3. I'm noticing that if I add or subtract these equations, I'm not going to eliminate anything. So I have to multiply one or both of the equations to do that. And I think I'm going to have to multiply both of the equations because 8 doesn't go into 5 and 5 doesn't go into 8 and 2 doesn't go into 3 and 3 doesn't go into 2. So I think what I'll do is I'm going to try to eliminate my y's here just because they're a little bit smaller numbers. If I multiply that by 2, it's going to give me a negative 6y. And if I multiply my second equation by 3, that's going to give me a positive 6y. And I like to have a positive and a negative so that I can add the two equations because I tend to make fewer mistakes when I'm adding. So distributing a 2, that gives me 16x minus 6y equals negative 22. And distributing the 3, 15x plus 6y equals a negative 9. Now notice that my coefficients of y are opposite, so if I add these two equations, I will eliminate my y's. So this is going to give me a 31x equals a negative 31, so x equals negative 1, and I will substitute that into any of my equations that I have there. Maybe I'll take my second one here, substitute negative 1 in for x. So I have 5 times negative 1 plus 2y equals negative 3, or negative 5 plus 2y equals a negative 3, and adding 5 to both sides gives me 2y equals 2, or y is equal to 1. So my final answer is the ordered pair negative 1, 1. And again, remember that means that that's the ordered pair that makes both of those equations true, and you can check by plugging in. And the last thing I want to take a look at here is a chart from your textbook that talks about different ways to solve systems of equations. We didn't actually go over the table method because that's not very good. Graphing is a good way to do it, but it's not going to be good unless it gives you an exact solution, unless those two lines cross in an exact point. Substitution works well if one of the variables in either equation has a coefficient of 1 or negative 1, then you would want to solve for that variable and substitute it into the other equation. Elimination using addition works well if one of the variables has opposite coefficients in the two equations. So for example, if you had a 3x and a negative 3x, then you could add those. Elimination using subtraction if one of the variables has the same coefficient in both equations. So like if you had a negative 7y and a negative 7y, you could subtract them, although I would prefer to multiply one of them by a negative 1 so you can add. And then elimination using multiplication like we saw in our last examples. If nothing else works, then you're going to have to multiply one or both of the equations by some number to get the same or opposite coefficients. So in this section we looked at solving systems of equations by graphing, by using substitution, and by using elimination. Recall that the solution to the system is the ordered pair that works in both of the equations and makes both of them true.